were mainly interested in using Jeopardy as a playing field upon which we could do some science. We wanted the ability to use questions that had not been designed for a computer to answer.
Jeopardy really represents natural language. You have to understand the English language and all the nuances and all the regionalisms and the slang and the shorthand to play the game, to get the clues. It's not just a piece of information.
This name of a boy who can fly can be applied to any emotionally undeveloped man. Christian?
What is Peter Pan?
Right.
Because the nature of the game, it's going to drive the technology in the right directions. It's got the broad domain aspect, asks all kinds of things, which is one of the challenges we really wanted to take on. It had the confidence aspect. Don't answer if you don't think you're right. You also had to do it really quickly, and we all knew that to make a technology work, it's got to be responsive. It had all the right elements to make a really good challenge to drive question answering.
The rate of growth of information is surpassing our ability to understand it and extract knowledge from it. We decided that we needed to build a system that could extract knowledge at a much faster rate from enormous amounts of data than human beings or any other computer system can do.
Resembling human conversation. It was a dialogue, you type things in and type things back.
How do you do? Please tell me your problem.
I'm feeling sad. Then it types back. Did you come to me because you're feeling sad?
Eliza was programmed to respond like a psychiatrist, but it had no real insight. Instead, it followed simple rules and rearranged key phrases.
So if I say, I'm dead, it responds, do you enjoy being dead? It doesn't have any understanding that dead is a different kind of condition. It really is just doing this sort of fill-in-the-blanks kind of pattern matching.
Anyone who tried to solve the language problem hit the same brick wall. The computer's profound ignorance of what we take for granted every day.
There's just so much more that we know that we don't know we know. I mean, just we know all kinds of stuff, like you press the up button in the elevator, that means it's going to go up. Or milk is white, or water is wet. I mean, there's just stuff that we know that we don't even realize we know. That's one of the things that makes it hard.
All the common sense knowledge a human brain collects naturally seems much too complex to program into a computer. But that hasn't stopped one scientist from trying.
So we have actually manually entered about 6 million rules. That's about 3% of what it's going to need to know in terms of actually spanning what you and I would call human common sense.
For the last 25 years, Doug Lynott has been leading a team trying to create human-like intelligence by teaching a computer common sense, rule by rule. The program is called Psych, and at headquarters the walls are covered with logic diagrams.
In a way, the magic of this, the power of this, is if you just tell it each rule one by one by one, and you give it general logical reasoning capabilities, that's all you need to do.
So far, Psych has 6 million rules and can answer a lot of common sense questions, like this one.
Can.
Psych says no, and it explains why.
Here, it's essentially saying the reason why cans can't can is that cans are inanimate objects, and it knows that can dancing requires at least partially having a brain and using it. It's just enough for Psych to get the right answer for the right reason.
25 years ago, many experts considered rules and logic the best hope for building artificial intelligence. But it's become clear these alone are not enough.
It's not just a matter of piling in more and more stuff. There are basic principles that we didn't understand. Putting in more and more stuff doesn't get you basic principles.
At IBM, as Dave Ferrucci and his team tackle the Jeopardy challenge, they know that facts and rules are just the beginning.
We couldn't write rules for every combination of word and phrases and context.
They need a new system, more fluid and flexible, to navigate the twists and turns of many different kinds of Jeopardy questions. They named their system Watson, after IBM founder Thomas Watson. The electronic Watson consists of 2,800 processors. That's like 6,000 high-end home computers. Altogether, it's the size of 10 refrigerators. The team starts filling his memory banks with about 10 million documents, most downloaded from the internet. Because when Watson plays Jeopardy, he must stand alone, just like his human competitors.
All kinds of content, okay, encyclopedias, dictionaries, thesauri, books, plays, you name it.
The entire World Book Encyclopedia, Wikipedia, the Internet Movie Database, much of the New York Times archive, and the Bible are just some of Watson's resources. And to build on Watson's foundation of data and rules, the team turns to a powerful tool in the computing world. It's called machine learning.
Machine learning is just like human learning from examples.
Before, people would just write rules by hand. Nowadays, it's all based on examples.
To understand how machine learning works, consider for a moment the letter A. What if you had to describe it to a computer? It's a real problem faced by the U.S. Postal Service, whose computers must decipher all kinds of addresses, printed and handwritten.
We all know what an A looks like. I know when I see it, but there's just way too many different types of A's. There are fonts where the A is just a triangle pointing up. Right? That's an A. Pretty quickly you realize there is no simple set of rules that you can write down currently for a program to determine whether a letter is an A or not.
Humans might not be able to come up with the rules that reliably identify all kinds of A's, but it turns out a computer can do it for itself, if you give it enough examples.
The way you do it is you just get an A, send it to the program, and say, that's an A. Here's another A, different one, that's an A. Here's another A, it's a different one, that's an A. Then you would give it another example, then you would give it another example, and you would do that 1,000,000 times.
The computer hunts for patterns among all those examples, and it finds them. So the next time it meets a letter A, even one it hasn't seen before, it will recognize it. This is machine learning, and it's a crucial element of Watson's programming. The team trains Watson. But here, instead of letters, the examples are tens of thousands of old Jeopardy questions, along with a cheat sheet of all the correct answers. Using machine learning, Watson will hunt for patterns between the type of question, the correct answer, and the kinds of evidence that support that answer.
Now, we do this over thousands of questions, so we come up with some way to weigh the evidence on average so that we come up with the right answer.
Now, when he's faced with a brand new question, Watson uses what he'd learned from these patterns and declares his confidence in each possible answer.
In the end, we get a list that says, here's the top answer, and we're 75% sure it's right.
Watson has now become a complex architecture of rules, raw data, and machine learning that enables him to use statistics to choose the right answer.
An IBM computer system named Watson won Jeopardy, but the real winner? Humankind.
Life is really about questions and answers. This technology can help us get some of those answers.
We're going to revolutionize many, many fields with this new capability.
Healthcare, government, finance, anywhere decision-making depends on deeper understanding of the huge wealth of information that's out there.
I thought the game was the end. I'm realizing it's just the beginning. That's what I'm working on. I'm an IBMer.